Okay, so to begin today, I want to set the scene again from the history of what's kind of brought us to this point. So, I mean, that's kind of been the goal of this whole unit is to walk our way from ancient theories on matter all the way up until right now. I want to begin our story again in 1939. Um, grade 12s, I'm looking specifically at you guys because I'm pretty sure you've covered this. What happened in 1939 that was so noteworthy world? Yeah, beginning of World War II, right? Do you guys cover World War II in grade 11 at all, or is that just grade 12? You guys do? Okay. So World War II starts. Do you guys remember why World War II began? Well, I mean, there's so many reasons, but like, what kind of kicked it off? Hitler invaded. Okay, I mean that's part of it. The main thing that kind of started the one I was going for here, because I don't think you could probably say there's one reason, but in September of '39, Hitler invaded Poland. Do you guys remember learning about that at some point? Yeah. Okay, so I want to bring the history, the social studies, into a little bit into our physics class today, because our story begins actually just before that. It begins in August of 1939, and so this is 1 month before Hitler actually invades Poland. And I'm sure that if you were to look it up somewhere, I'm sure they would have been planning their invasion of Poland for a while. So that was probably not, at least to Hitler, that probably wasn't a surprise. It wasn't like he woke up, you know, late September and was late August and was like, hey, let's invade Poland. They probably knew it for a while. But our story goes to August of '39, and I forget the other gentleman's name, but the main note is that Albert Einstein wrote a letter to the President of the United States, Franklin Delano Roosevelt, basically urging him to start working on nuclear technology. Basically, he said, if you guys don't start working on a nuclear bomb, Germany is going to, and that's going to be a problem for you. Does that make sense? And I think that was really interesting. And I don't know whether this is something you'd even learn in the social studies class, um, but that actually was a precursor to almost like predicting that all-out warfare was probably about to happen. I was reading up on this morning just to make sure that I could tell you the facts as accurately as possible. And I believe the way the story went is that it was actually 1 year beforehand in 1938 that three German scientists ended up discovering that they could break apart uranium and not just have uranium break apart due to alpha decay, but literally break it into two big pieces. And I'm going to flip to that in our slides actually here. Three German scientists, I've forgotten their name, but they managed to figure out that they could take uranium and they could split it apart into barium and krypton, and it released a huge amount of energy. Which, I mean, according to Einstein's formula E equals mc squared, we kind of realize that. But they discovered that they could probably weaponize this process and use it to create some sort of bomb. So, anyways, 1939, another gentleman, I forget his name. Feel really bad for the guy because he's a pretty influential guy in history. But anyways, he got Einstein to basically sign this letter to FDR saying, "You guys need to build a bomb." And the way the story goes, apparently, is that as the gentleman brings the letter to the president, he actually doesn't read the letter out word for word from Einstein. He kind of just gives the president kind of his own Cliff Notes version. And I think he kind of like he slow plays it a little bit, kind of saying, this technology, if we invest in it, it could be a source of power plants, and it could help out with medical technology. And I'm just envisioning FDR kind of sitting there going, yeah, who cares? That doesn't really matter, so stuff. And then he finally gets to the point, is like, oh yeah, maybe we could use it for a bomb. And at which point FDR kind of pipes up and says, so what you're really telling me here is that if we don't build this bomb, Germany's going to build it and kill us. And the guy's, yeah, that's kind of what I was coming here to tell you. That's kind of the picture that I kind of imagine getting painted. And that was really instrumental because that moment and everything going onwards from a physics and a social studies point of view, really that takes us up through so many years of social studies history. I mean, until nowadays in modern times, where I mean, I don't want to go too political now, but I mean, even just the fact that Donald Trump and Russia and the overlaps that they have right now, I mean, that to this day, it really still hasn't ended. That whole nuclear stuff. So today our goal, as you guys can probably tell where I'm going here, we're going to talk about the technology, the physics side of what makes up nuclear bombs. And this more or less ends the subject matter in physics that is concrete and fairly well understood by at least some people. I don't know that everybody necessarily gets this because I'm sure as we went along there were a lot of things where you're like, man, I don't understand. So now that's fine. Because pretty much the last topic we have after this is a very, very like maybe these exist. We're still working on that sort of stuff. So, anyways, this is kind of like the last sort of the last kind of frontier of where physics and chemistry have finally combined together to give us the last, I don't know, knowledge that we kind of teach in physics. So I'm going to show you about two reactions called fission and fusion. So basically anything nuclear, any sort of nuclear chemistry or nuclear physics, really this is where the two things they overlap, involve, well, obviously they involve the nucleus. Here are the two possibilities. Fission reactions involve taking a large nucleus and you split it into multiple smaller nucleuses or nuclei. Okay, and I already showed you that reaction. You take a large one like uranium, which has 92 protons, and you split it up. So one of them has like say 40 and one has 52. And by breaking that nucleus apart, it releases a whole bunch of energy. That makes sense? Now we're not talking just alpha decay. Alpha decay just means I'll pull off an alpha particle, which is just 2 protons, 2 neutrons. We're talking actually like literally splitting it into 2 semi-equal pieces. Okay. Now, most of the fission reactions that I've ever heard of, they're actually caused by a stable nucleus absorbing a neutron. And so I'll show you the mechanism for how they did this with uranium. But you basically, what you want to do is you want to take a nice stable configuration where you have 200 or whatever it is. Uranium is, what's the molar mass on uranium? Can you see it? 238 or something. Give or take? Yeah. So you got 238 particles all shoved together in a nucleus. And I mean, they're relatively stable. And all of a sudden, you shove in one more neutron. Well, all of a sudden, like it basically it can't handle it anymore, right? It's like the scale was able to handle this much. You throw one more on, and all of a sudden the stability breaks. And so basically, the glue that holds that strong nuclear force breaks into pieces and splits into two. Here's a downside, though. This involves nuclear waste. Fusion is something that I was also reading up on this. Fusion is something that physicists are still kind of working on perfecting. It is essentially what our sun does. It takes 2 small nuclei and it fuses them together into one big nucleus. Bigger nucleus. The most common one is basically take hydrogen and take another hydrogen and fuse them together and produce helium. Those are the 2 most common ways of doing it. One of the downsides to fusion is that it is very hard to contain. To my knowledge, when I looked it up this morning, and this can probably be changing by the day, there are really no pure fusion reactors in existence. Because in order to make a fusion reaction take place, it kind of requires an amount of input energy. Now, you guys took chemistry with me. Do you guys remember the concept of an activation energy? Like you have to input some energy to get it going. For you guys who haven't done chemistry, all reactions have what's known as an activation energy, a certain amount of energy to get it kick-started. For example, if you want to combust something, the activation energy is a match. You have to like strike the match, light that, and then once it gets ignited, then it can release more energy than you began with. Does that make sense at all? So, long story short, in order to kickstart a fusion reaction, it takes so much energy to get it going that my understanding is the only thing possible to get a fusion reaction to get started is a fission reaction. So if you want to set off a fusion bomb, you actually have to set off a fission bomb first. And so fusion is still being worked on to this day. So anyways, let me get through some of my notes here. So here's fission, and these are the 2 reactions that you're going to want to know about. The typical one involves uranium-235. Now, uranium in a 235 version is quite stable. It's actually there's nothing really wrong with uranium-235. But if you can throw an extra neutron into there, all of a sudden it becomes uranium-236, right? 1 extra neutron. And all of a sudden now it's unstable, and there's 2 different reactions. Doesn't really matter which one it performs. Both are just as fine. But the 2 different reactions end up causing it to split into multiple pieces. So here's the mechanism. Your uranium-235 adds the neutron, becomes uranium-236. It's now unstable, breaks apart, and here's where this works really well. It creates either barium and krypton or xenon and strontium. And if you guys look at the way that the math works out here, conservation of nucleons should be a thing, right? If you start with 92 protons, right here, these two numbers here, they add up to 92, right? If you start with 92 protons, these two numbers here add up to 92. But look at the top. You're now up to 236 total nucleons. 140 and 94 don't add up to 236, and 141 and 92 don't add up to 236, because it actually spits out 3 or 2 more neutrons. Well, this causes, and I've got it bolded here, what's known as a chain reaction. Because you got to think about this for a second here. This is just what happens with one particle. So let's say you have a huge sample of uranium, and you shoot 1 neutron at it. If you shot 1 neutron at your huge sample of uranium, then one of the uranium nuclei could break into pieces, and that would be it. It would happen once. Well, we've already done some math on this. I bet you that would give you 10 to the minus 11 joules of energy. And that would just happen for 1 nuclei. Well, that's not a bomb. You know what I'm saying? Like, that's not going to be nearly enough. Even if you had a massive, massive sample, if you shot 1 neutron at it, that's not enough. Well, then you might say, well, okay, well, let's just shoot a whole bunch of neutrons at it. Well, hang on a sec. Now think about the scope of that. If you wanted to work with, like, say, a mole of this stuff, you would need to shoot 6 times 10 to the 23 neutrons at this sample. That's not possible to shoot just that many. Like, that's a huge amount of neutrons. How do you isolate that many by itself? You know what I'm saying here? But this is where these particular reactions, they're not the only fission reactions that we know of, but they're the fission reactions that produce neutrons as a byproduct. Right? And so in doing this, what ends up happening is something like this. Here's a picture. You shoot 1 neutron at a nucleus. Well, that nucleus breaks into pieces. And I don't actually have a picture of the nucleus breaking into pieces here because that's not the point. But say it spits out 3 more neutrons. Well, then one of these neutrons can hit another nucleus. And then this one can hit another nucleus. Well, now these nucleus can split into pieces and create 3 more neutrons. Do you guys see where the phrase chain reaction comes from? All it took was 1 to get started. You don't need 6 times 10 to the 23 neutrons to actually have a mole's worth of uranium break down. You just need the 1, because the 1 spits out 3. This one spits out 3. In a way, this is an exponential reaction. For you guys who took my Math 30-1 class, this is like the equation y equals 1 times 3 to the x. You start off with 1 neutron, and then for every single one of these things that happens, you get 3 more. Right? So after you've done your first one, then you get 3. And then after the next one, you should have 9. Right? This picture doesn't show it right here, but if there was another nucleus here, you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, then the next one would have 27, and then 81. And you can see how this is going to multiply fairly quickly. Right? This is actually what becomes a huge problem if you're trying to harness nuclear energy. Today I'm going to talk about the 2 most common uses for nuclear energy. One, well, historically, since 1939, it was originally used to make a bomb. Right? Now, if you're trying to blow somebody up, you're not really worried about containing this. You just want to let it run and just explode, annihilate whoever you're trying to bomb, right? Which happened in 1945. You guys know the story of 1945? They dropped 2 bombs in, Hiroshima and Nagasaki, I think it was. All right, and, good news, bad news scenario. It did end World War II, but, it devastated certain parts of Japan, right? Anyways, if you're making a bomb, you don't really care about controlling it. You want it to blow up and wreak havoc, right? But if you're wanting to make a nuclear reactor, nuclear power plant out of this, you can't have it go blowing up and just melting down in the middle of wherever you have it, right? There's actually a very famous nuclear reactor that melted down. Anybody know the famous one in Russia? Chernobyl, yeah, where they weren't able to control it. Now, I don't know the exact details of the who, what, when, where, why. They may not even be available. That still may be secretive. Maybe it's online. I don't know. But yeah, that'd be a good example of how if you can't control your nuclear reaction and it gets away from you, then it's dangerous. That makes sense. So let me go back a slide here because I skipped one here. Here's a picture. Here's another example of how a nuclear reaction might look here. You have uranium adds the nucleus, the neutron gets to 236. It splits into 2 pieces, and it gives off 2.5 neutrons. Now that may seem kind of strange. You're like, how in the heck does it give away 2.5 neutrons? But hopefully I can explain that going back here again. There's actually two reactions that take place simultaneously. Some of your uraniums will turn into barium and krypton. Some will turn into xenon and strontium. Between the two reactions, this one gives off 3, this one gives off 2. So as an average between the two, it gives off 2.5. Does that make sense? So I don't know whether it's going to give off these two or these two, but on average, it gives off 2.5 nucleus or neutrons. Well, those neutrons then they make the next one happen and gives off 2.5 more, and it gives off 2.5 more. So that's the chain reaction concept. So, you guys feel like you get that concept of the chain reaction? Okay, so here's I'm just going to read off my slides. I don't do this a lot, but nuclear reactors, they need what's known as a moderator then, something to slow down the neutrons, because otherwise a meltdown process takes place. There was actually an issue with one of these in Japan a little while ago. You guys remember hearing or seeing that in the news? I think it was after a tsunami or after some sort of natural disaster that a nuclear reactor in the coast of Japan was having issues, and they were really worried about it going into some sort of meltdown. I don't remember exactly the details anymore, but do you guys recall this story at all? Anyways, I want to think there was an earthquake, and then it caused them to have some super huge problems, and they had to use a lot of ocean water to try to cool down the reactor and slow it down. Because if they didn't, then it was going to cause another Chernobyl, basically. So, anyways, it needs a moderator, and so there's a few different things you can use to slow down the neutrons. Because if the neutrons just fly free, you're going to have a meltdown, right? So, control rods are some of the possibilities. They could either use, say, boron or cadmium, and their goal is to absorb the neutrons. Right? And then what they do is they drop these rods down into the core, or they pull the rods out. So if you want to let it speed back up again, then you pull the rods back out, and the neutrons are allowed to fly free. It's getting away from you, drop these rods down into the nuclear reaction, and hopefully either this boron or this cadmium can absorb some of those neutrons. And then, all that happens is, say, boron's number 5 on the periodic table, right? Boron probably has a molar mass of around 11, so it probably has about 5 protons and 6 neutrons. Well, it just has 5 protons and 7 neutrons. No big deal, right? It just snags an extra neutron, right? Anyways, if the neutrons that are emitted are traveling too fast, another possibility is they use water to slow them down, which is why I just mentioned that I'm pretty sure they were using water from the ocean to try to slow down that nuclear reactor in Japan, and then there were some possible environmental issues with that. Anyways, here's how this works here. The hydrogen atoms in water then can absorb neutrons, and they can create what's called hydrogen 2. Okay. You know how hydrogen has 1 proton? Most hydrogens in the world just have the 1 proton. You know how the molar mass of hydrogen is 1.01? Well, if the molar mass of hydrogen is 1.01, it means that almost every hydrogen has 1 proton, and a few random ones out there might have a neutron, because that would give it a mass of 2, right? There's actually a couple out there that are actually found to have 3 total as their mass. So you could have a hydrogen that has 1 proton. You can have a hydrogen that has a proton and a neutron. Those are rare. And you can even have a hydrogen that has a proton and it could possibly have 2 neutrons. Those are even more rare, but these are the most common. And this has a mass of 1, this is a mass of 2, this is a mass of 3. So that explains why the molar mass of hydrogen is 1.01. It's mostly this. Anyways, what ends up happening is when you use water, the hydrogens on the water can absorb some neutrons, and it makes the neutrons, it makes it heavier, so then it's known then as heavy water. So that's another way of sort of slowing down a nuclear reactor is using water, and it creates heavy water. And what I've got on this next slide here is 3 different things that I've researched in the past that are used in nuclear reactors to slow down the neutrons. So in American reactors, they use what's known as enriched uranium, and basically what happens is they use more uranium-235, and so it just feels to me to be such an American thing. It's just like, let's just make it happen more critical reactions, even if neutrons are absorbed by water. They just, in case the water is absorbing too many neutrons, they just use whatever is known as enriched uranium. In Canada, we actually have what are known as the CANDU reactors. Have you ever heard of these before? And CANDU stands for Canadian Deuterium Uranium. And so what they do is they use heavy water already. And so if they use heavy water, then it means that it can't absorb neutrons because it's already heavy. So these are ways to like prevent the slowing down of neutrons, by the way. And another thing that you can use is graphite rods in either Russia or the UK, but apparently those will burst into flames possibly. So now I have to admit here, I'm not a nuclear physicist. If I was, I'd be working in some sort of probably top secret lab somewhere, and you know what I mean. Like, there's not a lot of people on the planet who actually do this sort of stuff. I think for two reasons. One, you actually have to know what you're doing. And two, if you do what you know what you're doing, you possess the knowledge to create a weapon of mass destruction, and we're as a society we're trying to prevent that. You know what I'm saying here? So knowledge on nuclear bombs, although I'm sure you can read a ton on the internet, is not exactly something that like is everyday sort of knowledge, right? At least not like the nitty gritty specific specs on that. So I only noticed a little bit. Like I just know the basics. Here's something that you need to be able to do. If I give you an equation, I need you to be able to calculate how much energy a nuclear bomb or a nuclear reaction can create. So, we've actually done this before. What's the process by which we're going to calculate this? How are we going to find this? Find the mass. The mass before and the mass after is going to be slightly different. Why? The binding energy in the nucleus. Yeah, that binding energy, however the heck that strong nuclear bond works, that missing energy, according to Einstein's formula, is going to be converted into, well, that missing mass is in the form of energy, right? So, oh, why don't we stop for a second? There's muffins, yogurt, fruit. Out of curiosity, when you guys do talk World War II and on, when I talk about the Cold War, do you guys talk a lot about nuclear side of things in social studies? Is that a big piece of what you've done? You guys didn't?
Like we just talked about like
The threats of it. So I mean, the you talked about it a little bit. So okay. I mean, this is where I think this is kind of. I hope this doesn't come off as being uncaring, but I think this is kind of cool. The overlap between physics and social studies because this is relevant. You know, like a lot of times you might say, "When am I ever going to use this in life?" Yeah, this matters. The idea of nuclear technology, the threat still hangs over our heads, right? I don't think it's actually cool the idea that we could die to a nuclear bomb. Hopefully, you don't think that's what I'm saying, right? But I think that like the overlap between the two subjects, and this is a time where it actually like yeah, there's similarities between physics and socials, right? Maybe you don't think of that so much. Oh yeah, let's give this one a try. You need to in your notes find that table that I pasted in your notes from a while back because you don't have this in your data booklet. So you'd have to be given a table like this that gives you the masses of all sorts of different nucleus. You guys know which one I'm talking about? In topic 4, about 3 or 4 pages in. So again, this is stuff that you'd have to be given a table for, but it's definitely a possible type of question. So if I look up uranium-235 on this table here, it weighs 235.043930. And I'm not going to write the unit next to it, but that's in the atomic mass units. So that's not kilograms yet, that's just U's. Okay, then a neutron it's 1.67, but it's more than that. It's 1. Actually, why don't I use its U version? Actually, it's 1.008665. And then while I'm doing that over here, why don't I draw this one as a 3 times 1.008665. Krypton, that's what, Krypton 92? Krypton 92 is 91.926156. And then barium 141. There it is. 140.914412. So again, just to make sure you're clear, this is not something that you'd be able to do without the assistance of some sort of table. But it's very possible that they would give you this information in a table on a test question. So long as you're able to use this. One more thing, they might not give you the neutron though, because technically you have the mass of a neutron in your data booklet, only you don't have it this precise. You only get it at a couple sig digs. So long story short, I need you guys to add this up on both sides and calculate the mass defect, because there should be a slight amount of missing mass. Okay, I calculated a loss in mass, or a mass defect, so I'll write it as change in mass. I'll write it as 0.186032. Let me know if anybody doesn't get that, or does get that even. You got that? Okay, that's a good sign. Okay, let's give everybody a second to make sure you catch up to that. You guys feel like you are able to replicate this on your own? Okay, so if that's your mass, now keep in mind your units. I did all of this in what's known as the atomic mass unit, which is going to need to be times by 1.66 times 10 to the minus 27 to get this into kilograms. So I'm just going to write it as A kilograms, and then to get the amount of energy that's released, it'll be mass times the speed of light squared. So I'll just do the rest of my calculator. Times that by 1.66 times 10 to the minus 27, and then times by the speed of light squared. Now, I didn't get very much. I got an energy unit, again, of 9.26 times 10 to the minus 20. Oh, and I didn't times by the speed of light squared. I take it back. I got, it's still not a whole lot. I got 2.78, let's call it, times 10 to the minus 11. And that would be joules, because we were in kilograms. You got that as well? Okay, same logic as before. That doesn't seem like a lot of energy, right? And if the reaction was not set up the way that it is, where the reaction uses a neutron, but also produces neutrons, if that didn't work, what would happen is you'd shoot one neutron, one particle would break into pieces, it would release a small amount of energy, and we'd be done. And that'd be really boring. We wouldn't be able to do anything with that, right? But because the reaction produces more neutrons, now for every single nucleus, you would get that amount of energy, right? So imagine that we were to use 1 mole of uranium. 1 mole of uranium weighs about 235 grams. So hypothetically, let's say that you could get a hold of 235 grams of uranium. Now, you and I shouldn't be able to do that because it's very restricted. But you know, the U.S. government and different countries around the world are stockpiling their uranium, trying to get their hands on it in case they want to make a bomb out of it. Hopefully they don't. But I mean, you guys have heard that phrase, nuclear stockpiles? Right. So if you can get your hands on 235 grams of uranium, then you'd take that number there and you'd times by a mole. So I'm just going to times this real quick by a mole. 6.02 times 10 to the, 23? Well, all of a sudden now, if you had 1 mole, which is 235 grams of uranium, and all of it reacted, you'd get 1.67 times 10 to the 13 joules. That's actually a staggering amount of energy from 1 mole's worth. Right? In terms of perspective, I believe a giga is times 10 to the 9. Do you guys have a table? What's times 10 to the 12? What's the next unit up from 9? Is it tera? Tera? So if tera is times 10 to the 12, that would be 16 terajoules of energy. That is a huge amount of energy, right? All released just by this 235 grams of uranium, which again, civilians should not be able to get their hands on that, but there's going to be some governments that definitely have that much, right? And if you put that into a nuclear warhead, that's going to level a city, right? Now, by the way, one more thought here. If you guys haven't heard this, when nuclear bombs go off, not only does it release this amount of energy, but it also releases gamma radiation. Because what ends up happening is the nucleus. Where's that good picture here? When the nucleus breaks into pieces, right here. Remember how we learned yesterday that when a nucleus has to rearrange itself, it gives off gamma radiation? Apparently, if the nuclear bomb didn't destroy everything just based on the amount of energy released, everyone would die due to gamma radiation poisoning anyways, because it releases that much gamma rays on its own as well. So nuclear bombs are like doubly destructive. One, for the energy output, just due to releasing bonds. Two, due to the energy, the EMR that's released due to gamma radiation. So, yeah, these things are devastating. All right, any questions? Okay, let's talk a bit about fusion. Now, when I made these notes, it was 2 years ago, and things kind of changed. I did a quick Google search this morning. To the best of my understanding, fusion is still not attainable on its own. Because really, what's happening is you're making a sun. Okay, that's what happens in our sun. Hydrogen and hydrogen fuse to form helium. And so what ends up happening is as the hydrogen nucleus forms together, they form a helium nucleus. And then actually what ends up happening is the four hydrogens have a little more mass than the helium, so the missing mass is energy. But I believe this is still true as when I wrote it here. Scientists have not figured out the bugs there. They can build and run a fission reactor, but they haven't been able to figure out how to run fusion just yet. Now, fusion bombs exist. In order to make a fusion bomb work, apparently you need to make a fission bomb set off the fusion bomb, which just sounds insane. Because a fission bomb, we just saw, gives off, like, just even a small amount of it gives off huge amounts of joules of energy. Why would you need to use a fission bomb, to set off a fusion bomb to get more? Like, isn't the first one destructive enough on its own? Right? Like, it's totally overkill. But, if you ever heard of, like, an H-bomb or a hydrogen bomb, a hydrogen bomb essentially is the fusion bomb. Now, when I was in university, I remember my professor telling me about how they were working on trying to do cold fusion, which, again, to the best of my understanding, is still like just a hypothetical. But the idea would be if you could get cold fusion to occur at a lower temperature, then you wouldn't need to hypothetically set off a fission bomb because you need high temperature and high pressure to make this work. But like we'd have to set off a sun on Earth, right? Like that would be very, very, very dangerous. So cold fusion would be trying to do it without that at like a very low temperature, and it hasn't been achieved to the best of my knowledge yet. So, anyways, here are some of the reactions that take place because it's actually not just one. When we talk about it, we make it sound like just two hydrogens form a helium, but apparently there's multiple reactions. So here are some of them. Take two hydrogens, and then what ends up happening is it forms a hydrogen and a beta particle and a neutrino. You guys remember that notation from the other day there? This is a beta particle, which is an electron, and a neutrino, and it forms something different here. Well, what ends up happening is this hydrogen and this hydrogen, this one's a hydrogen 1 molecule, this is a hydrogen 2. Oh, by the way, did I mention the name we give to the hydrogen 2? It's called deuterium. Did I have that somewhere here? Deuterium is the 2 version, and tritium is the 3 version. Oh, here it was. Deuterium. Deuterium is hydrogen 2, where it has one extra neutron. Tritium, by the way, tritium, is the name given to hydrogen 3. Very, very rare. I mean, as rare as it is to have a hydrogen with a neutron, a hydrogen with 2 neutrons is even more rare. So, okay. Anyways, where was I? What was I talking about? Oh, this guy right here. So this is a normal hydrogen. 2 hydrogens come together, and they they form this particle right here. Now I take it back. I lied. This isn't an electron, is it? What is this particle here? This is a B with a 0 and a 1 on the bottom. If it's a 0 and a 1 on the bottom, that's a positron. Yeah. So what ends up happening is the two hydrogens, which are basically a proton and a proton, they come together and somehow they spit out a positron so they can get a neutron out of this thing instead. So it spits out a positron, an antineutrino, and it makes the heavy version of this. Well, then the heavy version of the hydrogen fuses with an original hydrogen again to form a helium, plus I believe this is some gamma radiation. Then the heliums, two of them come together to give a hydrogen, to form a regular helium, one that has two neutrons, not just one, plus it also spits back out a hydrogen. Anyways, long story short, when they combine all these reactions together, this is the net of those reactions. Now, you guys did chemistry. Do you remember what it's called when you take like multiple reactions and you add them together? What we called that? There was a special name for it. It was a law. Nice, Tesla's law, yeah. Essentially what happens is if you combine these four reactions together, this is the net chemical reaction behind it. It basically involves four hydrogens all together, coming together and fusing to form a helium. Now that might seem strange because you're like, hang on, four hydrogens is four protons. How can four protons form a helium that only has two? Well, you can see right here. It actually forms two positrons, two neutrinos, and 7 of whatever this thing is. That might be the symbol for gamma radiation. I don't know. Crazy stuff. Anyways, it releases a lot of energy. So, here's a slide I found on the internet that kind of shows the difference between the two. Nuclear fission then takes a neutron, add it to U-235 to make it 36, splits into pieces, gives off more neutrons. Okay. Fission is splitting. Fusion involves taking two particles together and fusing them to give one thing, and then it just so happens that it actually, when it does that, it splits back into smaller pieces again, but it did fuse. So here's a slide that also does like a, what would you call it, like a Venn diagram kind of thing, similarities and differences, compare and contrast. So here's the main thing to know. Fission needs a chain reaction. Fusion requires extremely high temperature, which is why you need to use a fission to make a fusion. This has not yet to be developed. This one here does occur, but it creates nuclear waste. One more thing here, the raw material for fission either involves uranium or possibly plutonium. Those things are very strictly controlled now. You can't get your hands on that stuff. Right? There's actually only a few countries in the world who possess it. I think I have a slide on my next one here that show it. But off the top of my head, like United States, Russia, United Kingdom, France, they all possess nuclear stuff. Recently in the news, maybe you guys remember hearing about this, Iran ended up getting nuclear capabilities. Israel, I believe, has it as well. And the other big country in the news that's kind of an iffy one, North Korea, as to whether or not they actually possess or don't possess nuclear capabilities. Because I don't even think Canada actually has like stockpiles of uranium. We might, I don't know. So I found this picture online. I don't even get how it works, to be honest. Like I said, if I did, I wouldn't be working as a high school teacher, right? So I mean, I can look stuff up online. I can remember information, but this apparently is what a nuclear warhead would look like in order to create a hydrogen bomb. It actually needs to have uranium in this one right here somehow, I guess, in order to cause like some plutonium or something else to happen. But I don't know. I found this picture online. I thought it was cool. This is a nuclear bomb. Oh wait, here's a picture I have that is old. This was 2012, so I'm sure this has changed, but countries that possess nuclear capabilities, US, Russia, UK, and France. So those are the ones I mentioned. Israel, Iran, and then yeah, this is the one that I guess we'll see what ends up happening over the next little while with Donald Trump. And have you guys like heard things on the news like this? Yeah, I mean it's still topical today. So I mean, even as I started our story in 1939 with Einstein writing FDR saying you should build a bomb, it still matters now. Here's a slide I found that this is terrifying to me. This is all of the supposed nuclear facilities in the United States. Yeah, like that's just like a, Are you kidding me? There are that many? So this is locations of nuclear weapons. Like, there's one in Montana, apparently. Are you kidding me? Nuclear weapons plants and labs. There's quite a few here, and then all over the east coast there, they have a whole bunch of nuclear power plants, right? Which I mean, so long as they're safe and they don't melt down, I guess no big deal. But I mean, there's a lot of nuclear technology all over the United States. It's crazy. Yeah, like some of them are weapons, some are plants, and then some are actual like power plants, right? But like that's a lot. The crazy thing is like all of these nuclear warheads that are just kind of scattered around like the United States here, just maybe waiting to be launched. You teach social studies, right? Just wondering whether you can add something that I can't here. We're talking about nuclear technology from a physics point of view. What sort of treaties have been signed since the Cold War, do you know, that have been used to try to like reduce the amount of nuclear warheads? Okay, that was the one that came to mind. I don't know much about it. Could you add something for us? Okay. So it's like a containment concept. It's like if someone. So how did this Iran stuff work the last little while ago? Since we're talking topical stuff with Obama and you know what I'm talking about? I wonder whether that's this maybe the slide I had right here that I found. A lot of geopolitical. So what about nuclear disarmament stuff? Like what's happened in terms of that? Do you guys talk about this in social studies? Do you know? This one here. Yeah. Okay. And I imagine things like submarines and ships. Yeah. They're probably the closest one to be able to make it there. That makes sense. I was gonna ask because I thought I had read somewhere that like there were agreements where okay, we get rid of five, you get rid of five, we get rid of two, we get rid of two, kind of things like that. Okay. Okay, well, I got one last slide here, and then I got some practice diploma questions. Thank you for helping me out here. I was just telling these guys beforehand, this is a kind of a cross-curricular day because we're doing physics and social studies. So, last thing here, here's a timeline, which is probably still obsolete because you can see it only goes up to 2009, but of just when nuclear technology was used. And I mean, we're talking all the way back to 1945, right, where we started our lesson, right? The idea of the Manhattan Project needing to, Einstein saying, FDR, make a bomb. You're going to need one in case Germany makes it first. And so here were the first ones that were made. And your timeline goes all the way through the Cold War, all the way up through, I mean, the last one on here, 2009, just like we're kind of saying here. Does North Korea have the ability to make bombs? I don't know. I think that is that confirmed, probably.
Well, they can't launch
Right, because they've been doing those tests that were
yeah,
unsuccessful.
speculations that the West is
Fair enough.
they what North Korea does is
Mm, fair enough. So just like I said, this is why I don't possess that knowledge because I'm just a high school science teacher. I know a little bit. So okay, let's do some practice questions. You guys don't have these, do you? Okay, so let's try some diploma type questions on. This is on the whole unit though. This won't just be on nuclear stuff. This will be on everything. So let's try one here. You've got white light going through a glowing solid, and then it goes through a cool gas. Oh, thank you.
have fun, guys.
What kind of spectrum does it give? You have white light going through a cool gas. This is a straight up knowledge one, eh? Absorption. Yeah. Let's go back here in our notes. I'll find it in our notes here. It's going to be a while back here. Now, we talked about emission spectrums and absorption spectrums. Oh my goodness, how far back do we need to go now? How many slides do I give you guys? I do my best to prepare you. Okay, somewhere around here we would have talked about Bohr. And this was an emission spectrum and this was an absorption spectrum. So let's talk about this for a sec here. An emission spectrum occurred when we added some energy to something, and then it caused the electrons to hop up an energy level and then come back down again. Right? And when something was heated, and then the electrons excited and then de-excited, it released energy. Right? But what ends up happening on an absorption spectrum is that if you were to pass white light through a gas, what really ends up happening is that light, as it hits the gas, it can bump the electrons up. But then, you know how the light normally would be every sort of color is white light? Well, those specific bands are now meeting because those wavelengths are the ones that were used to knock the electrons up and back down again. You get what I'm saying here? So if you shine regular light through something cold, the cold gas will absorb just a few specific frequencies. And yeah, so this right here would be you heating up hydrogen gas. And then this right here would be you use cold gas and you try to pass light through it. Almost all of the light makes it through except for these few bands right here. So one of the things you guys are going to discover in this unit here, as much as any other unit, you're going to want to do a lot more reading than before. Like if you guys aren't reading your textbook, you really should, because you might find just little things that are worth remembering. This is probably a little bit more like how lab teaches bio, probably. Like there's not a lot of concepts of math behind it. It's all memorization of what we've learned. Okay, let's try another one here. Planck introduced the idea of quantum nature of light. Why? To account for the behavior of blackbody radiation, to support Maxwell's theory of electromagnetism, to account for wave natures of the electrons, or to support the concept of a nuclear atom. Why did Planck introduce the idea of quantum? I mean, all of these things we've talked about, none of them are necessarily wrong, but why did Planck, what problem was Planck trying to solve? Okay, nuclear atom. Timeline. That's 1939. That's not it. Wave nature of the electron. That was afterwards. That was Young's double slit experiment. That was later. Maxwell's theory of electromagnetism. Well, that was before, but that's still not what we were looking for. It was that black body problem. The idea was that things should keep emitting radiation further and further as you go up, but it stopped. Remember the name for that? It was called the ultraviolet catastrophe. This was what he was trying to stop there. All right, what else do I got here? here's a radioactive decay curve. And for those of you guys in my 30 level class for math, this should scream exponential graph, right? All we got to do is interpret it. We want to figure out the half-life of polonium-210. Here is where we were at 100. Well, half of 100 is 50. When does 50 occur? After, let's call it 100 and I think it's 140. You guys see that? If I were to drop it down properly, straight down here, that's 100 and that's 200. I think it's going up by 20, so that's 100, 120, 140, 160, 180, 200. So that would have been 140 days. That makes sense? Just purely based off a graph. Okay, this is on what we talked about today a little bit, the theory behind it, not so much the history. I like the social studies overlap, but you're not going to get tested on like the Cold War, right? But I think it's worth knowing. Right? Okay, anyways, two deuterons, so this is like deuterium, the heavy hydrogens combine to form helium. Approximately 24 mega electron volts of energy is released. By the way, you guys remember talking about mega electron volts yesterday? It's another version of energy. Okay, anyways. Possible explanation for the release is what? Do the two deuterons have a greater total mass than that of the helium nucleus? Do they have a smaller total mass than that of the helium nucleus? Do they immediately break apart, or are they more tightly bound to the nucleus? Hopefully right off the bat you can actually narrow it down. It's one of two. It's A or B. Right? It's got to be about that released mass. We just got to figure out, is it greater or less? So let's talk through this here. If you have this guy here, and a second one of this guy here, and it eventually forms a helium nucleus. For there to be a release of energy, it means that this mass right here must not equal this mass right here. They must not equal, right? Which side has the more mass, though? Well, it better be the helium side right here, because there must be a missing amount right here that then got released. Does that make sense? This side right here, whatever mass you have right here, is not the same as the mass you have right here, because for some reason this one's heavier here, right? And so these guys right here, that missing mass must be in the form of energy. So which one's right then? The two deuterions must have a smaller total mass than the helium nucleus. There must be some extra mass here found in the form of energy, and when it forms this one right here, that energy is then going to get released. Okay, here's one that's really based more on our previous unit. You've got orange light with a frequency, and we've got a work function. We want to find the maximum kinetic energy. Well, we've done this before. Your kinetic energy is really equal to Planck's constant times by the frequency minus the work function. You guys remember that formula there? I mean, more or less, it's all ready to go here. Here's your frequency. Here is your work function. However, can you use them directly as they are, those numbers? Well, I guess you could actually. Planck's constant, though, use the 414 number, and then that would give you energy in electron volts. Anyway, so you guys, let's not bother solving. You guys know how we'd solve it, right? Okay. Okay, this next one here. The nuclear reaction above, is it alpha, beta, fission, or fusion? Fission. Isn't this what we just talked about today? Take your uranium, add a neutron. Now it skipped the intermediary step, but it's splitting up into two pieces. Right? That's not the same thing as alpha and beta decay, right? Alpha and beta involve just pulling off a small piece of it. This is breaking it up into two big chunks. Okay, here's another one. Household electricity causes very weak electromagnetic radiation throughout your house. I mean, just by having the lights on, there's EMR being produced. Why? Well, there's a changing electric field, which then causes a changing magnetic field, which then causes a changing electric field, which then causes a changing magnetic field. Anyways, can you guys see where I'm going with this? There's a lot of theory questions. Well, not necessarily a lot of math as we get forward here. I mean, there's some. There definitely can be some, but not necessarily a lot. Here's a math one, though. We've got a particle traveling at a certain velocity and entering a magnetic field, and I give you the magnetic field strength. The particle travels inside the magnetic field with a circular path of a radius, and we want to find the charge to mass ratio. Follow-up question. Who did this experiment? Who did this experiment? Who found the charge to mass ratio? Oh, this is good. J.J. Thomson. Thomson did the charge to mass ratio. Is that what you're going to say? Okay, so this was Thomson's experiment. So let's do his math. His math was that mv squared over r must be equal to qvb. But at the time, he didn't know mass or charge. He was missing both of those. So instead, he found a charge to mass ratio, and he rearranged the formula by bringing this mass down to the bottom here, canceling this v with that one there, and bringing this field down to the bottom right there. So all you literally have to do on this question is take this velocity, divide by that field strength, and divide by that radius, and you've got your charge to mass ratio. It's actually really, really easy. But you have to know what you're doing. I can totally see this having been a question which actually asked you as a follow-up whose experiment it was. Because that's something you need to know. You need to know these scientists. Okay, here we're giving you a frequency. Small flashes of blue light can be observed when air bubbles in water are exposed to ultrasound. And the frequency of the ultrasound of the blue light that you get is this frequency here. So we want to figure out how much energy is required to produce the photon of it. What formula are we going to use to solve this? Yeah, E equals HF. Now, really, it's E equals NHF, but we're just going to make it one photon, that's all. So, I mean, you've got a frequency. That'll give you a energy. Except if you want it, and make sure you watch really carefully, if it's in electron volts, make sure you either convert the frequency or the energy somehow, or a better option, just use the other Planck's constant. Makes sense? Follow-up question for this one could have been, who came up with this formula? Max Planck. By the way, those are the things I want in your timeline. Oh yeah, gallium-75. Ooh, I've talked to you about this question before. Gallium-75 decays by beta emission to make an unidentified daughter nucleus expressed as ABCD. That's my first question here. Who is the daughter nucleus if you have beta emission? So let's write this out here. Gallium-75 is a 75 on top for gallium. We need a periodic table. Can you just see back here? Can you find where gallium is? What number is it? Good, 31, yeah. And by the way, you guys do get a periodic table. I haven't printed you one yet. Okay, well, if gallium is going to undergo beta decay, what does a beta do? What is a beta particle? What are the numbers we put on a beta? 0 and -1, yeah. Because what ends up happening is a neutron converts into an electron and a proton. So it's still going to be a 75 on top, right? But what happens to the bottom number? 32. It goes up by 1. Because -1 and 32 is the 31 there, right? So then who is it? 32 would be germanium. So anyways, the way this would work would be 7, 5, 3, 2. Does that make sense as the way that they'd assess that? I was describing to this one to you guys earlier. Now, the other thing it says here is it's got a follow-up one here. I didn't keep reading here, but it says the beta particles produced in this decay have an average energy of this much mega electron volts. And then it says the distance the beta particle can travel in air depends on its energy. The range for beta particles is approximately this many meters per mega electron volt. Now, this would be like a kind of a new and unique kind of question. We've never seen one of these before, because it says, well, how far away should you stand so that you don't get hit by a beta particle? Anyone have any ideas how you do that? How would you solve this? I mean, this isn't something I taught you. Yep. That was it, yeah. Because this is how far it travels per mega electron volt. This is how many mega electron volts you have. So, I mean, if you really wanted to write it out, it would be like this. 3.65 meters per mega electron volt. And then it releases 3.39 mega electron volts. Times those two numbers together, That'll get you how many meters you need to stand away. So, I mean, roughly, I don't know, 10 to 12 or something. This would be a good example, though, of like, they're going to throw a little twist at you haven't seen before. Okay, that's all I got for today. We have one last lesson, and we're done physics. This last one's the really strange stuff. So that's kind of a preamble. We're going to talk about antimatter, like the negative doppelganger versions of things, the positrons, the antineutrinos, that weird stuff. And we're going to talk about what are called quarks, which is what scientists believe make up the subatomic particles. So, like, what is an electron made out of? What is a neutron made out of? The theory is, not to spoil the lesson here, but where's the picture I have of one of these here? Here's a picture. This right here is thought to be what a proton is. And a proton, the theory is a proton is not just one thing. Apparently they think a proton is made up of like smaller pieces than that. Some of them have like what are called partial charges, like 2/3 of a charge or negative 1/3 of a charge. And so this kind of breaks Millikan's theory that like the smallest charge is 1.6 times 10 to the minus 19, because physicists are always trying to work on, well, what's smaller than that and what's smaller than that. So anyways, that's kind of the idea of string theory is, well, what's the smallest things made out of? So, okay, anyways, I'll stop it there. You guys have any questions? Okay, last thought. There's 5 things to work on. Quiz and a unit test come after our break. So the main 3 things you guys should be working on in your spare minutes here and there are your video assignment, your assignment, and your timeline. And I put a couple of due dates on there just so that you guys don't like procrastinate. I want to keep you on schedule because I think that when I wasn't giving due dates over the last little while, it wasn't helping. So they're not necessarily all that soon, but let's put some days on here for when I want things to be done by if you can omit them. So sound good? Okay. Well, you have like 10 minutes left to kind of work on a few things here and there.